we will learn the rectifier with filter capacitor. As we have seen in the last two videos, in half wave rectifier and full wave rectifier, the output that we are getting, that is not resemble to our the DC output voltage. So we are going to add a filter. So what will be the function of a filter? It will try to decrease the uncertainty of this. If this is my output, there are some various variation over here. So the filter will try to limit this variation. So we'll see how. So by adding a capacitor in our either in half wave rectifier or full wave rectifier, that will make a filter. So let's see what is the function of a capacitor, how it works in a rectifier circuit. Let's take for a starting case without taking any load. Let's just connect a diode along with a capacitor. This is my input voltage. Okay, this is the diode, this is the capacitor. We are not connecting any load. We are going to see what will be the effect of capacitor over this circuit. Then in the later case we will add our load, that is a resistors in parallel with this capacitor. So let's see. This is the input voltage, which is nothing but my sinusoidal signal. Okay, for the positive half cycle of this input signal, this will become plus, this will become minus. Now this diode is in forward bias because P side is connected to positive side. So the diode will start conduct. Now let's take it is an ideal diode. So what is the characteristic of an ideal diode? That is the VD value is equal to 0. That means just at this voltage also at starting, from starting the diode will start conduct. As this V increases beyond 0, the diode will start increases. The diode don't need any value of like this doesn't, this 0.7 value is not required for the diode to conduct. Okay, so that's why the ideal diode. Just taking for our assumption for our easy clarification. Let's see what is happening. So as this voltage increases, the diode is forward biased. It means the diode will become short circuit. Okay, for the positive of the diode becomes short circuit. So this capacitor will charge as this voltage increases. The capacitor will charge. So if I draw my output, since there are no other component, whatever be the output voltage, which is nothing but the voltage across capacitor. So from starting 0 to till the maximum point, that is nothing but Vp. If this is my Vp, small p, my input signal, this is the capital V, capital P, which is nothing but a peak value. So the capacitor will charge till that point, till the peak point, my capacitor will charge. Okay. Now the capacitor charged to the maximum value is nothing but V peak. So my V output is nothing but V peak till this point my output is nothing but V peak. Now as this voltage decreases than V peak, these values are less than V peak, then what will happen? This was a diode over here. Now the cathode side of this diode, which is nothing but a peak value of Vp. Okay, and since there are no other circuit, the charge will remain stored over here. And the anode side, the positive P side of this diode, which is nothing but a value less than Vp. I am talking about these points. For these points, this side of this diode having a value less than Vp, and this side having a value Vp. It means the diode is in reverse bias because N side with a high value, P side with a less value. Since this diode is in reverse bias, then what will happen? Since this is ideal diode, for reverse bias the diode will off, means open circuit. Then what will happen? The charge which is stored till this point, that charge will continue till over here. Okay, because there is no path to discharge capacitor, there should be a path, then only capacitor will discharge. Since there is no path, the charge will stored in the capacitor. Okay, now for the negative half cycle, this is negative, this is positive. Then again the diode is in open circuit, means in reverse bias, so it is open circuit since it is ideal. So what will happen? The charge which is stored in the capacitor, which will not discharge, so it will maintain a value of constant value of V peak. Okay, from starting to here the capacitor will charge, and after that the diode is in reverse bias, so it is total open circuit, so the charge stored in the capacitor will maintain a value V peak. That's why this circuit, this diode and capacitor is called a peak rectifier. Peak rectifier or peak detector. Why this name? You see, the output is maintaining a value of Vp, maximum value V peak. Okay, this ideal diode with a capacitor will maintain a value V peak throughout this Like since there might be some positive half again, but the capacitor will again this, what will happen if you will come over here, again the charge is positive till this point also, this region, what will happen, this diode is reverse bias because this side value is less than Vp, because this is my Vp and this side value is maintaining a Vp. So what this value, this P side of this diode won't increase than Vp. That means this side will be always higher, this side will be always less. So the diode will be always in reverse bias. That's why the capacitor will maintain a charge. That's why this is now name called peak rectifier or peak detector. This was the ideal case. Now let's take some practical case where there is a load which is connected with the capacitor, and let's see the behavior of that. So what we are going to do? We are going to add a resistor in parallel with the capacitor, and we are going to take our output across this resistor. Okay. Now for the positive half, I am removing this two diagram and drawing it once more again here. So this was my previous case. This is my input. This was my output for the ideal case. It was maintaining a value V peak. It is output. This is my Vp. Means this is the input voltage which is nothing but Vp. And this is a function of time. It is also a function of time. Okay. Now we are going to see for practical cases. Now, as this voltage is for the positive half of my input, this is plus, this is minus. The capacitor, the diode is, we are taking here the diode is ideal, so that we can get a better result. We can examine bit more clearly. So since this voltage just increased beyond 0, the diode will conduct and it will become short circuit. So for the positive half, the diode is become short circuit. Okay, this is for the positive half. This path, lower path is for positive half. So the capacitor will charge. So the capacitor will charge till this point. Till this point, my capacitor will charge. Now, as this voltage decrease bit less than Vp, now it is charged to Vp. This voltage will decrease less than Vp. This means this diode is now in open circuit. So the diode is now in open. Which is the path? Which is the lower path. So since this is open circuit, what will happen? The charge stored in the capacitor, it will try to discharge. Since a resistor is, a load is connected across here, through which this charge will discharge through this capacitor. Okay, the charge will discharge through the capacitor. What will happen? The charge which you are getting, the output voltage. Okay, for the first case, it is fully charged. The output voltage was nothing but Vp. So let's check. So what will happen? Now my charge will start decaying through this resistor. The charge will start decaying. Okay, the charge will it will decay through this resistor. Now let's take a value over here. This charge will this capacitor will discharge till a value over here. Now, as this input voltage, again, now the charge which was before some Vp, it was the case for Vp. Now it is decreased a bit less value than Vp. Now when my input increased above this point, then what will happen? Again this side will become more positive. This side is less positive because some charge is already discharged through this resistor. So this value is less than Vp. Now this value is bit less than Vp, but this value is more bit less than Vp. It is the value, suppose this is a value which is nothing but Vp minus 3, let's take, and this value is nothing but Vp minus 2. So when this is Vp minus 2, this is Vp minus 3, means it is the becoming a forward path, forward bias. So this path will conduct current again. So what happen again? Since this path will conduct, the capacitor will again charge. So the capacitor will again charge a value over here till Vp. The capacitor will again charge. Now it is fully charged to Vp. Again this value which is nothing but Vp minus 1. Let's take a value Vp minus 1, bit less than Vp. So what will happen? This side is positive, that is Vp. This side is less than Vp. So this, it will again become a reverse bias. So what will happen? My capacitor will again try to discharge till the next cycle of this value of next cycle. Till this value it will start to discharge. Okay. So this is the characteristic of our output, which will behave like this. It will charge for this small interval and it will discharge for the almost for the time period. If you will see, from here to here, it is my time period. So from here to almost this point, this is the time period. So capacitor is discharging for the almost time period, that is dt, that is t period. Okay, this is the case where my capacitor will charge from here. If I will take just this much value, you will see from here to here, it is charging for a small interval which is nothing but t1, and this is t2, and discharging for a long interval t. Till this point it is discharging. So what is my del t, which is nothing but t2 minus t1. For this much interval it is charging only. Okay, and for this interval my diode is conducting, and for the rest interval the diode is not conducting. Let's understand this point a bit more clearly. If I take an example of a, let's take what I can say. Let's take a, suppose this is a glass. A glass, okay, and here it is a jug. A big jug which is full of water. So this is a jug which is full of water, and this is a glass which is now empty. Okay, now here is a, suppose a man over here, and which is what drinking, which will drink water with a straw. Okay, now this is the what input side which is having a high amount of voltage. So this jug is full of water. Now at some case this diode conduct and the capacitor charge. So what will happen? Now this jug, what is, it is filling the glass. So it is filling, slowly filling, it is completely filled. Okay, now see the charge which is completely filled till the Vp. This is the maximum value, which is nothing but the jug has water also, and this is the maximum value of glass which can contain. So this is the value of Vp. Let's assume this is a capacitor, and the water inside is nothing but the charge stored in the capacitor. So now the capacitor is fully charged. Okay, now what happened? We are connecting a resistor. So let's take this man which is act as a resistor. What he is doing is drawing the water. He is drinking through the straw. So the capacitor charge discharge. If you remember, once it is charged, this is positive, this is negative. How it will discharge? It will discharge through this. It will discharge. This is the property of a capacitor. It will charge from positive to negative, and it will discharge in this way. It will change its polarity to negative to positive and discharge in this way. So the man, now it is drawing. So since it is drawing water, what is happening? The water level becoming bit less. So you can see over here, from here to here, since the this is the area which is filling at a high rate, but since the straw is very small, that will draw only small amount of water. So this is the man which is drawing water from the glass. So it is taking much more time, but only small amount he can draw. So this man through the straw is drawing very small amount of water. Okay. Now what happened? Again a case arises when this value reached where my jug will again start filling. My jug will again start filling the glass. Again it will start filling, again filling. So the water it will not reach maximum value. It will not reach maximum value because this capacitor, this man is drawing water through this. So this value, which is nothing but, if this is my Vp, maximum value which is Vp, this is the Vp. So this value the man is drawing. It means through the resistor that charge is storing, that charge is discharging. So it will again reach a value Vp. This jug water is reaching, and it will again reach a value Vp. So when this is Vp, so it is fully charged. So no water can be poured into this water, into this glass. So this is the maximum level, that is Vp. So what will happen? Again this part is left, and the man again start drawing. So this process continues. It will fill and the man will draw. It will fill, the man will draw water. So similarly it is filling till the maximum charge, and the man is drawing the water till this point through the straw, and again it is drawing, it is reaching to the maximum charge, that is fully water, the glass is full. Now it is the man is drawing. Okay, so this is the characteristic of if you see the output that we are getting in normal half of rectifier, which was nothing but this value. This was my output. Now if you compare, it is bit close to my DC value or not. Since okay, this is the value, this discharge, which is nothing but very small, for very small voltage, as this man is drawing very small amount of water, which is nothing but my voltage. Charge means I can write in terms of Q equal to CV. So in charge I can write dQ by dV. That means this is the voltage. If this is my peak voltage, this is V peak. So from peak some voltage is left. So V peak minus VR, which is nothing but my V output. Okay, this is the V peak value, and since it is decreasing, this is the VR, means very small amount of voltage which is dropped. So V peak minus VR is nothing but V output. Since this value is very small, this VR is very small, the water drawn by the man is very small, this V output is approximate to V peak, means my maximum voltage. So I can draw almost a straight line. It is not ideally I can say a straight line, but practically it is not there. It is some fluctuation is there. I said that time the ripple, but this is the variation of charge with respect to time, that is called ripple. So this VR, which is not to ripple voltage, from here to here, this is called ripple to ripple voltage, which value is very less. Okay. Now we have in our design we have to keep a point in our mind that this C value should be very high. How? If this C value will very high, my R into C, which is called time constant for RC circuit. When a RC circuit is there, the tau is tau. It is the time constant for RC circuit. It is the way of decaying. This RC value should be very greater than the time period of this signal. The time period of our input signal, this RC value should be very high. Why? If my RC value is very high than T, then it will not decrease much more. Okay. If my RC value is very less, then what will happen? This might be the case. If my C value is not taken a very high value, if my C value is very less, then what will happen? The charge through this resistor will decay in a high rate, or it might reach to a value 0. So it will not behave as a DC voltage, because it is charging again here, again here, again here. So this is not reasonable. It was the case which is this. This is the both cases are same. That's why our C value should be very high, so that our RC, which is nothing but the time constant of this circuit, should be greater than equal to T. If we will, while taking the value of C and R, if we will make this point clear, then this decaying would be very less. As you see, this value, it is seems bit high, but this B value is very less. It means this value and this value is not much more difference. This value are almost close. Okay, this is the charging point, this is the discharging point. So this is the maximum value, this is the point T2, as I told you, this is the point T2. So how to know that how much my capacitor charge? Just make my ID 0. If I will make my ID, which is nothing but a current across the diode, if I will make my ID 0, it means this is the reverse bias. As you remember, for this case, as this is my ID 0, what is happening? The maximum charge stored across the capacitor that we are getting. So how to find this T2? If I will make my ID 0, I can know that how much level my capacitor can charge. Okay. So you remember this interval del T, the diode is conducting only for this interval, and it is conducting how? It is charging the capacitor to such an extent so that it can discharge for a long interval T. For a long interval T, it can discharge. It is charging. Means this jug is filling the water, that much water which the man is drawing. It means it is filling less 10 unit, then the man is drawing 10 unit. It means the amount which is drawn by the man, that amount is filled by the jug. Here is the same. The amount which is discharging throughout this time period, capital T, this much amount of charge is replaced by this diode for this small interval. Okay. So these are some points you have to remember in your mind. So this is, you can see now our output, which is bit resemble to our DC voltage. If I draw, this is my DC voltage for half wave rectifier. I am saying this is my DC voltage. This DC voltage is bit close than this value as compared to this. Here there is more fluctuation. Okay, so that's why we are using capacitor as a filter. Now later we will see the use of voltage regulator in some next chapter, that how this voltage regulator can be connected in across this after this filter circuit, so that it will get me a value of this. So this is the case for half wave rectifier. Similarly, if I will take the full wave rectifier, a diode connected over here, a diode connected over here, and a resistor over here, and a center tap transformer is there, and across that resistor the capacitor value should be there. So my design will be like this. Here one diode will be there, here it is the center trap, here the resistor, here the capacitor, and here again a diode should be there, and here it is a center tap which is tapped at the center. So this was the case for center tap rectifier, or in bridge rectifier also. If you remember, this was the circuit for bridge, which looks like a Wheatstone bridge. So this was my resistor. So across the resistor, if I will connect a capacitor, it will again be like a this filter circuit. Okay, so for that case, my output, if my output is like this before connecting this capacitor, for after connecting the capacitor, how it will become? It will become like this till this point. again charge till this point, it will discharge, feed charge. Okay, so that can more resemble to a DC value. So this is all about this capacitor filter circuit using the rectifier. Now let's see one more application of this diode half wave rectifier that we left in our previous chapter. We are going to see that one, that is called precision rectifier, or that is called SUPERDIODE. Let's see that one. Okay, so what is a precision half wave rectifier or precision rectifier, or that is called SUPERDIODE? If you remember in our half wave rectifier, if this is my half wave rectifier and across which suppose a resistor is there and a voltage source is there, when this diode will work, let's take for practical cases, not ideal cases. For practical cases, when my voltage Vs, when this voltage is greater than Vt or equal to Vt, okay, if this will be the case, then my diode will start conduct and it will flow current through the resistor and will get the output. There are certain applications in which we need our rectifier to work at a voltage of 100 millivolt. Let's some application in which our this rectifier circuit, half wave rectifier, should work in an input of a voltage of 100 millivolt. Then this diode won't work. If I will give 100 millivolt over here, this diode will not on, because this diode need 0.7 volt. This diode need 0.7 volt to operate, and I am giving 100 millivolt, which is nothing but 0.01 or 0.1 voltage, whatever the value, which is very less than 0.7. So the diode will not conduct. So since, but what we have to do? We have to work our application. We have to use that diode in our application. So what we can do? If you remember in our op-amp that we read, but if you are giving a small input of signal, and because of the op-amp open loop gain, that output of op-amp is getting bit high. What is the for ideal op-amp? What is the for ideal op-amp? What is the open loop gain for ideal op-amp? Open loop gain, which is nothing but infinite. Or some practical case, let's take a value 1000. Okay. If I am giving a input 0.001 of voltage, of this much voltage at input side, what I will get at output side? I will get a output side of value this much input difference between two terminal multiplied by the gain, which is nothing but 3, it will become 1 volt. You see, I am giving 1, this is 0.1 millivolt, 1 by 1000. It is 1 millivolt. I am giving 1 millivolt at my input side, and what I am getting? I am getting 1 volt at output side. So this is the function of the op-amp. So what we are going to do? We are going to add this op-amp with our this diode. If we are going to add this op-amp with our diode, then it will act as a rectifier also for a small input. Let's do that. Okay, now tell me, this is which type of op-amp? It is a non-inverting op-amp. My input is given to the positive terminal of this amplifier. So it is a non-inverting op-amp. Okay, now you see, when this diode will conduct, when the voltage across this diode, Vt will greater than or equal to 0.7. As we know, for our constant voltage drop method, this voltage across diode is 0.7. So when this voltage will at this Va, then only the diode will conduct. So how to get a value, Va value? My V input value should be bit higher than the diode voltage drop divided by the gain. Are you getting or not? I need a voltage over here. This value should be equal to diode voltage. My Va, which is nothing but Vid multiplied by gain. This Va, that is the output of this op-amp, which is nothing but difference between two input and multiplied by the gain. Okay. Now this is the voltage required for the diode to operate. Now if I divide this value by A, then what will happen? This value will cancel. So it will remain only Vid. And for now, this case, my input is nothing but given to my positive terminal. So my Vi value should be bit higher than Vid, or in any way I can say Va or Vt, same case. So this input value should be bit higher than the drop of this diode divided by the open loop gain of this diode, of this amplifier. If my input will be this value bit higher than this value, then the output, let's take a value, my diode need Vd value is equal to 0.7. Okay. So when this value will, this Va is bit higher than 0.7 or equal to bit higher than 0, then the diode will conduct. Let's take my Va value 0.71. Okay, this much value is enough to operate the diode. So this is the voltage at this terminal. So this Va 0.7, how I will get this 0.7? If I will give a input voltage 0.0071, this is my input voltage. This value I will divide by a value. If this is 0.071, I will multiply this value, input value, multiplied by the open loop gain, which is nothing but 1000. Let's take 100. 1, 2, 3. It is 71 by 10 power 4 multiplied by 10 power 2. Okay, if I multiply this 100, which is nothing but the gain of my operation amplifier. So this 100 is nothing but the gain of my op-amp. If I multiply this gain with this input value, this is the input value, the small value. You see, this is the 0071. If I multiply this gain with a high gain, that is 100 or 1000, I will get the output value 0.71, and this much output at op-amp is enough to operate this diode. Okay, so now you can see with a small input, this is now 0.0071, this much small input is enough to act as a rectifier. Okay, as this diode will conduct, then the current flow, so it will become a negative. You can see this is a negative feedback path. It will become a feedback path. This output of this op-amp and the negative terminal of this output of this diode and the negative terminal of this diode. The output of this diode and the negative terminal of this op-amp. It looks like a feedback path. Okay. We know for our virtual short circuit, whatever the voltage over here, that will be the voltage over here. Whatever the voltage, because of this two terminals, this voltage should be equal. Then only it will make a virtual short between two terminals. So since this is input, this is also a V out, Vi. So my VIE is almost similar to V output. Okay. So if I draw a input and output characteristic between my V input and V output, it will pass, not exactly pass through this center, but it looks like a straight line value pass nearly to the center, whose slope is equal to nearly 1 by 1. And here my output is nothing but input. And if I give a input like this, then I will get my output. For half wave rectifier, I will get a half wave, and for full wave, I will get a full wave rectifier. So this is the input versus output, and here see both input and output are same. Okay, so this part is called the SUPERDIODE. Why SUPERDIODE? Because the diode will conduct only when the 0.7 voltage is applied to its input side. But here you see a input of 0.0071 volt. This much small value of input is enough to act this diode. That's why the name SUPERDIODE. Okay. It is called precision half wave rectifier because for a small input, a small value of input, it is working and it is rectifying our output. Our output is rectified of this input, so that is called precision rectifier, half wave rectifier, or we can call this as a SUPERDIODE. So how to form a SUPERDIODE? We have to connect a op-amp with a diode, and when this voltage is positive, means this value is for positive value. So this diode, this op-amp will work. This is positive means I will get a output which is nothing but positive, and this positive means my diode will conduct, and I will get a output. For this case, my Vi equal to, if this is my input, my Vi is nothing but my V output, same. Okay, and when this input is negative, so what will this op-amp? It will become negative input multiplied with the gain. So this output will become positive for first case and negative for second case. That much value, I will get a 0.71 voltage at the output, but that value is negative. And since this is negative, so the diode will not work. For the negative, it will become reverse bias. So the diode is open. So the output, my output is 0 for that case. And this op-amp will behave like this open loop gain. It is the open loop behavior of op-amp when for the negative input is given, and for the positive input, it will again op-amp will conduct a value of positive, and this diode will conduct, and we will get an output which is nothing but same as input. Okay, almost similar to input. So this is a rectifier which work with very small value of input. And before what we read, that was for working for very high value of input, 20, 30, 40, many high value of input. Then only the diode will conduct. and this diode is conducting at very small input, which is for our application, as I told, I need 100 millivolt. For this much input, only this diode can conduct. Okay. So this is the all about till this point we have read that diode, half wave rectifier, full wave rectifier, precision rectifier. There are certain topics that is related to clamping and limiting circuit that we have read in op-amp, that our output of op-amp will limit till this value. We won't get this maximum value. Okay. This op-amp need two power supply we read before, plus VCC minus VE. Here I am not showing because just it will make the circuit become more complicated. But this op-amp need two battery sources, two supply to operate. Okay, DC supply to operate. So don't forget this two while drawing this. This is the supply that is the op-amp needed. Okay. If you remember in our op-amp circuit that our output voltage will limit till this point. This is L plus upon A. This is L minus upon A. That is some two terms were there. So this is the limiting circuit. Our output is limit or it is clipped. So this term is also there in our diode case, but for our exam point of view, it is not required for now. But after completion of this chapter, of this first module, or after the completion of the whole basic electronics chapter, I will try to follow this limiting and clamping circuit. These two parts we will read after this syllabus. Okay.